All right, let's take a deep dive into intuitionism. A fascinating, really fascinating area of math. We're going to be talking about L.E.J. Brouwer. Um, he completely rethought what math is. And you know you're coming at this as a philosopher, so we're going to really get into like why Brouwer thought the way he did.
Yeah, what's so interesting about Brouwer is that he wasn't just content to like do math within the system that everyone had, agreed on. He wanted to like question the whole foundation of the field. Like why are we even doing this? And so that led him to develop a whole philosophy of mathematics.
And that's intuitionism, right? Like it's not just different
Yeah.
theorems, it's like a different way of looking at what math is.
Exactly. So to give you some context, imagine you're like a normal mathematician working in like, what we call classical mathematics, and you come across some mathematical statement. Even if you can't prove it or disprove it immediately, you just assume that it's either true or false, right? Like in some absolute sense.
Okay, yeah, that makes sense. Like there's an answer out there, we just don't know it yet.
Right. But Brouwer comes along and he's like, wait a minute. What if the truth of a mathematical statement isn't like pre-existing? What if it's something we actively construct through our mental activity?
So we're not discovering truths, we're creating them.
Hmm.
That's a pretty wild idea.
It is. And it all stems from Brouwer's philosophy of mind, which was really heavily influenced by thinkers like Kant and Schopenhauer, who, they really emphasized how our minds shape our experience of reality. And Brouwer just took that and was like, all right, I'm going to apply this to math.
So this is where the philosophy comes in. So how
Yeah.
did Brouwer's like journey begin? Where did this all start?
Well, it's interesting because even in his early work, like his dissertation in 1907, he's already kind of poking at the foundations of classical mathematics. One of his big things early on was that he took issue with Georg Cantor's theory of transfinite numbers.
Oh yeah, Cantor. He's the guy who came up with the different sizes of infinity, right?
That's the guy. So Cantor's theory was really groundbreaking, but Brouwer argued that these like higher number classes, these infinities beyond infinity that Cantor was proposing, he's like, those can't be constructed mentally. So for Brouwer, if you can't construct it in your mind, it doesn't exist mathematically.
Because he's not saying that Cantor is wrong. It's more like they're playing different games with different rules. Like those transfinite numbers just aren't relevant to his system.
Yeah, that's a great way to put it. So like that rejection of transfinite numbers, it really highlights the core difference between intuitionism and classical math. It all comes down to what the mind can construct.
Okay, so let's get into that a little bit more. What does it actually mean to construct a mathematical object in your mind?
It means you have to be able to demonstrate its existence through some kind of step-by-step process, a sequence of mental operations that anyone could follow.
Okay, so it's not enough to just like define something abstractly. You have to show how to build it, like brick by brick, but with thoughts.
That's a perfect analogy, yeah. And this leads to what's called constructive mathematics, where proofs are not just about logical deduction, they're about actually showing how to build the thing you're talking about.
So that's really different from how proofs work like in regular math.
It is. In classical mathematics, you can prove something exists without actually showing how to find it. Like you can use proof by contradiction, where you say, okay, let's assume this doesn't exist, and then you show that that leads to something impossible.
Right, right. I remember that from logic class.
But that wouldn't work in Brouwer's world.
Not at all.
Right. For Brouwer, a proof has to be constructive. It has to give you a recipe, an algorithm for how to actually make the object. It's not enough to just argue that it must exist out there somewhere. You got to show me how to make it, mentally speaking.
Okay, this is starting to click. So if everything has to be constructed mentally, what are the building blocks? What are like the fundamental objects that he works with?
All right. So this is where things get even more interesting. Brouwer introduces this really powerful concept called choice sequences.
Choice sequences. Okay, I've heard of those, but I'm a little fuzzy on the details.
So imagine a sequence of numbers, but instead of it being like predetermined, you're choosing each number one after the other as you go.
Okay.
So that's a choice sequence. It's dynamic, it unfolds in time, and it really reflects like the activity of the choosing subject.
So it's not just like a list of numbers, it's a process.
It's a process, exactly. And here's the really mind-bending part. Brouwer uses these choice sequences to represent real numbers, which, those are like the basis of calculus and analysis and all that.
Wait, he builds real numbers from these choice sequences.
He does. And that leads to some conclusions about real numbers and the continuum that are very different from what you get in classical mathematics.
Okay, this is fascinating, but I do want to ask you a little bit about Brouwer, the person. What was he like? Because it takes a certain kind of person to like challenge the foundations of math like that.
He was a bit of a maverick, like, very strong personality. He was known to kind of go against the grain. He even had some famous clashes with other mathematicians, like David Hilbert.
So he was kind of a fighter, too, not just a brilliant mathematician.
Oh, yeah, he was very passionate about his ideas and not afraid to defend them, even if they went against the grain.
He's like, I'm not going to play your game. I'm going to make my own game with my own rules.
That's a great way to put it. And those rules, as we're seeing, they lead to a very different way of looking at math, a way that's centered on what our minds can do and the power of construction. So we were talking about how intuitionism really puts mental construction at the heart of mathematics. To really see how different that is, let's get into those choice sequences and see how they change something as basic as real numbers.
Okay, yeah, let's do it. You mentioned before that Brouwer uses choice sequences to represent real numbers, but
Yeah.
but how does that actually work?
It's a little tricky at first, but let's try to break it down. So in classical mathematics, you usually think of a real number as like a point on a number line,
Hmm.
or maybe an infinite decimal expansion.
Right, like pi.
Yeah.
3.1415, and on forever.
Exactly. But Brouwer's approach is much more dynamic. It's like imagine you're constructing a real number using a choice sequence.
Okay.
You start with some rational number, like let's say 1, and then you have to make a choice. Do you go up or down? Let's say you choose up. Now you have to choose how much to go up. Maybe you choose 1/2, so now you're at 1.5.
Okay, I'm following so far. It's like I'm choosing a path on the number line, making choices at each step.
Yeah, that's a great way to think about it. And you just keep doing that, potentially forever. You're making choices and narrowing down the interval where your number could be.
So the real number is the limit of this process, the
Mhm.
point that I'm getting closer and closer to as I make more and more choices.
You're getting there, but there's a crucial difference. See, in classical math, that limit already exists, even if we haven't calculated it yet. It's a fixed point. But in Brouwer's system, the real number only comes into being as you make those choices. It's not like it's pre-existing. It's being constructed step by step.
Wow, so it's like the number is constantly in motion as I make more choices. It's not like it's just sitting there waiting for us to find
Look,
it.
exactly. And this has some wild implications. For example, in Brouwer's system, not every real number actually has a decimal expansion.
Wait, really? How is that possible?
It all goes back to that idea of construction. You see, in classical math, you just take for granted that every real number has a decimal expansion, even if you can't write it out.
Yeah.
But in Brouwer's system, you have to actually construct that decimal expansion using your choice sequence.
And sometimes you can't.
Exactly. Here's a crazy example. Imagine a choice sequence where each choice depends on the answer to some unsolved math problem. So let's say if the problem turns out to be true, your sequence will give you the decimal expansion of pi. But if it turns out to be false, it'll give you the decimal expansion of, I don't know, the square root of 2.
Okay, so it's like the choice sequence is in limbo until we know the answer to the problem.
Right. And here's the thing. Until that problem is solved, we can't actually say what the decimal expansion of that choice sequence is, because those choices haven't been made yet.
So it's not just that we don't know it, it's that it doesn't exist yet until we make those choices.
Exactly. And that's a really striking example of how Brouwer's focus on construction leads to totally different results than classical mathematics.
Mm-hmm.
And it also ties into how he challenges something called the law of excluded middle.
Right. That whole idea that a statement has to be either true or false.
Yeah.
It's like he's saying, well, hold on, what if we can't prove either way? What if we're stuck in this in-between zone where we don't know the truth yet?
Exactly. And that challenge to the law of excluded middle, it has big implications for how logic and reasoning work in a Brouwer's system. But it also has some interesting effects on things like calculus and analysis.
Okay, so how does something like calculus change? When you build it on this idea of choice sequences and this rejection of the excluded middle?
Well, think about how we define continuity in normal calculus. We say a function is continuous if you can draw its graph without picking up your pencil.
Right, that's kind of the intuitive picture. But how does that translate to Brouwer's world?
Well, in Brouwer's system, continuity is all about how choice sequences interact. A function is continuous if it maps nearby choice sequences to other nearby ones.
Okay, I think I need a little help with that. What does it mean for two choice sequences to be nearby?
Imagine you have two choice sequences that are being built at the same time. They start at the same point, and for the first few choices, they make the same decisions. So their paths are really close together.
Okay, so I'm picturing like two lines that are kind of tangled up together, at least for the beginning.
Yeah. Now, a function is continuous if it takes those two nearby choice sequences and it sends them to new ones that are also nearby.
So it's like it preserves that nearness. It doesn't create any sudden jumps or breaks.
Exactly. And what's really amazing is that Brouwer proved that in his system, every single function from the real numbers to the real numbers is continuous.
Wait, hold on. Every function. But I thought there are tons of functions in regular math that have discontinuities. You know those jumpy graphs that you learn about in calculus?
That's true in classical math, but those functions rely on things that aren't valid in Brouwer's system. They often involve the law of excluded middle, or proofs that kind of cheat by assuming things exist without actually showing them.
Right, because you can't just say something exists, you have to show how to build it.
Exactly. And when you stick to those rules, you end up with this really strong result that all functions have to be continuous.
Wow. Okay, so in intuitionistic analysis, it's not just that some functions happen to be continuous.
Yeah.
It's like it's a fundamental rule. It's built into the system itself.
Yeah, that's a great way to put it. And it has some really interesting consequences. Like in classical calculus, there's something called the intermediate value theorem. It says that if you have a continuous function that takes on two different values, then it has to hit every value in between.
Right, right. So if you're drawing a curve from one point to another, you can't just jump over any values in between.
Exactly. But the normal proof of that theorem relies on the law of excluded middle, which Brouwer doesn't accept. So in intuitionistic analysis, the intermediate value theorem doesn't always hold true.
So there are actually theorems that are true in normal math, but not in intuitionistic math.
That's right. And that shows how Brouwer's ideas aren't just about proving the same things in a different way. They actually lead to a whole different set of mathematical truths, a different way of understanding what these concepts really mean.
That's incredible. Okay, so we've seen how intuitionism changes analysis. What about other areas? You mentioned topology before. How does it work there?
Well, Brouwer was one of the founders of modern topology in classical mathematics. He came up with lots of important ideas and proved lots of big theorems.
Right, so he mastered the game before deciding to change the rules.
Exactly. But but his intuitionistic ideas lead to a totally different understanding of topological concepts. Things like continuity, connectedness, dimension. Like in classical topology, we might define a continuous function as one that preserves something called open sets.
Open sets, right. There were those sets where every point have a little neighborhood that's also in the set.
Right. But in intuitionistic topology, we have to be really careful about how we define those things. We can't just rely on normal logic and set theory. We have to build them up using choice sequences and all of Brouwer's tools.
So you're rebuilding topology from the ground up using Brouwer's principles.
Exactly. And that leads to some really cool stuff. For example, in classical topology, there's something called Brouwer's fixed point theorem, which says any continuous function from a disk to itself has to have a fixed point, a point that doesn't move when you apply the function.
Right, that's the one about stirring a cup of coffee. There's always got to be at least one point that ends up right back where it started.
That's it. But the normal proof of that theorem uses techniques that Brouwer rejected. So in intuitionistic topology, you have to come up with totally new ways to prove it, or find a weaker version of the theorem that works within Brouwer's rules.
So even a theorem named after Brouwer might not be true in his own system.
That's right. It just shows how radical his ideas are. It's not just about changing the methods. It's about changing our whole understanding of what mathematical objects and concepts really are.
This has been such an amazing journey. I feel like I've learned so much. But before we wrap things up, can you leave our listeners with a final thought? Something to think about as they keep exploring this amazing world of intuitionism.
Intuitionism really makes us rethink the connection between math, the human mind, and the universe. If mathematical truth isn't something absolute and unchanging like Brouwer thought, but something we actively build with our minds, well, then what are the limits of that creativity? Could it be that reality itself is a mathematical construction, like the product of some cosmic mind that's constantly making choices and shaping the universe?
Wow, that's a really mind-blowing question.
Yeah.
And it's definitely one we'll keep wrestling with as we explore the mysteries of math and the universe and how our minds fit into it all. Thanks for taking us on this deep dive. Okay, yeah, I think I've had a minute to digest all that. It's amazing to think that Brouwer's ideas about mental construction and choice sequences, they could lead to such a different view of math. But I'm curious to see how these ideas actually work in practice. Like you mentioned that intuitionism has influenced what's called constructive mathematics in fields like analysis and topology. Can you give me some examples of how that works?
Yeah, definitely. Let's start with analysis, which, as you know, deals with things like continuity and limits and calculus. One of the most interesting results in intuitionistic analysis is something called Brouwer's continuity principle, which says that every function on the real numbers has to be continuous.
Wait, really? Every function, but we were just talking about how regular math has all these functions that aren't continuous. You know, those jumpy graphs with breaks in them?
Right, that's true in classical math, but those functions, they depend on things that aren't allowed in Brouwer's system, like the law of excluded middle or proofs that kind of assume certain points exist without showing how to get them.
Right, you can't just say something exists, you have to be able to build it.
Exactly. And when you work within those rules, the whole idea of continuity starts to mean something different. Like in regular calculus, you might say a continuous function is one where you can draw the graph without picking up your pencil.
Right.
But in intuitionistic analysis, it's all about how functions act on these nearby choice sequences.
Oh yeah, we talked about that. But can you remind me what it means for two choice sequences to be nearby?
Sure. So imagine two choice sequences that are being constructed like step by step. If they make the same choices for the first few steps, then their paths will be really close together, like at least in the beginning.
Okay, so they're kind of like intertwined, like two vines growing up a trellis or something.
That's a great image. So a function is continuous in Brouwer's system if it takes those nearby choice sequences and maps them to new ones that are also nearby. It preserves that nearness without creating any jumps or gaps.
So in intuitionistic analysis, it's not just that some functions happen to be continuous, it's like a fundamental rule.
Exactly. And that has some really interesting consequences. For instance, in classical calculus, there's a theorem called the intermediate value theorem, which says if you have a continuous function that takes on two different values, it has to hit every value in between.
Right. Like if you draw a curve from one point to another, it has to pass through all the points in between.
Exactly, but the standard proof of that theorem uses the law of excluded middle, which Brouwer doesn't like. So in intuitionistic analysis, the intermediate value theorem isn't always true.
So there are some theorems that work in regular math, but not in intuitionistic math.
That's right, and that shows how Brouwer's ideas aren't just about finding different ways to prove the same things, they actually lead to different mathematical truths, a whole different way of understanding what these concepts mean.
That's incredible. Okay, so we've seen how intuitionism affects analysis. What about other areas of math? You mentioned topology earlier. How does it work there?
Well, remember, Brouwer himself was one of the main people who developed modern topology in classical mathematics. He came up with a lot of the key ideas and proved a lot of the important theorems.
Right, it's like he mastered the game before changing the rules.
Exactly. But his intuitionistic ideas lead to a very different way of understanding topology. Things like continuity and connectedness and dimension. For example, in classical topology, a continuous function is one that preserves something called open sets.
Open sets, right. Those are the sets where every point has like a little neighborhood around it that's also in the set.
Right. But in intuitionistic topology, you have to be much more careful about how you define open sets and neighborhoods. You can't just rely on normal logic and set theory. You have to build them up using choice sequences and Brouwer's other tools.
So you're basically rebuilding topology from scratch using Brouwer's ideas.
Exactly. And it leads to some really interesting results. Like in classical topology, there's a theorem called Brouwer's fixed point theorem, which says if you have a continuous function from a disk to itself, there has to be at least one point that stays fixed.
Well, the one about stirring a cup of coffee.
Yep, that's the one. But the usual proof of that theorem uses techniques that Brouwer didn't accept. So in intuitionistic topology, you'd need to come up with new ways to prove it, or maybe find a weaker version of the theorem that works within Brouwer's rules.
So even a theorem named after Brouwer might not actually be true in his own system of math.
Yeah, that's right. It shows how radical his ideas are. It's not just a minor tweak to classical mathematics. It's a whole new way of thinking about what mathematical objects and concepts really are.
This has been an incredible deep dive. I feel like I've learned so much. Thank you so much for walking us through this fascinating world of intuitionism. And to our listeners, we hope this has sparked your curiosity about the surprising connections between math, the human mind, and maybe even the universe itself.